So today, I did want to talk about one more thing before I formally get into the algebra. I'll say something about that in a moment. So, actually, that's the question. Let me point this out here first. This we know, right? We know that there's a one-to-one map from the natural numbers into the reals, right, for sure. And we've also shown that, so we will show. We've got that. Everybody agree with that? So that gives less than or equal to. We also know this from the homework, right? You could use, like, for example, a tangent function or something like that with this. And there exists no bijection G from the natural numbers into 0, 1. So this shows that the natural numbers are not equal to reals. So here's what we know. We know the natural numbers are smaller than size, less than or equal to anyway, reals. We know that they're not equal to, because we've shown that, right? That was the counter diagonalization. And so by the comparability theorem, if you believe the axiom of choice, which we are going to in this class, this is your only option, right? This is a smaller size. Here's my question. Call it S. This is, I think, kind of the next natural question. Is there a size of infinity that you can squeeze between the natural numbers and the bigger infinity real numbers? Okay, let's take a vote. How many of you think we can do this? How many of you think we can? I'm a glass half full kind of guy. You're all wrong, and you're all correct, right? Services. The answer is it's actually been proven. So what that means is the axioms of set theory, even with the axiom of choice, do not tell us enough about sets to answer this question. It has actually been proven this cannot be proven with current axioms. So what does that mean? That means that no matter how hard you scratch this problem, you are never going to be able to come up with a proof that this can be done, nor will you ever find a counterexample. Because there are certainly not enough axioms, or there's not enough there. This is called the continuum hypothesis. So I'm gonna do this loosely, no size of infinity. Between n and I have seen, it has been shown that this is independent of the axioms of set theory that working mathematicians today use. I have seen talks where people say, okay, this can be shown using the continuum hypothesis. If we assume that the continuum hypothesis is true, then we can prove this theorem. What does that mean? That means they weren't able to prove it using the mathematics that we use. What do? They threw in a new axiom. So not only did they use choice, they used continuum hypothesis and they proved it. They are correct in the sense that what they proved will be consistent in our mathematics, and it will probably not work if they assume the negation of the continuum hypothesis. Because if you can do it, assume both that and negation, it must have been true in the original. In fact, here is one of the things that's true, and this kind of set a lot of mathematicians, sent them to the suicide hotline back in the 20s, because there's a famous result by Godel that says, actually it says something much more general than this. But if you ever make mathematics with a finite list of axioms, and let's face it, the axioms are the things that you kind of assume without really right. You gotta have some starting ground. You're certainly going to want a finite list of axioms, otherwise you'll never start doing mathematics. You'll have to list it for many of them, right? If you have a mathematics that you make with a finite list of axioms, you can always formulate a statement in that mathematics that can be neither proven nor kind of counter-examined. And this is an example of one in what is used in the current state of mathematics. Now, here's what makes that scary. I may spend 10 years trying to prove some theorem that I want to prove, and it might be undecidable. My personal experience is that it's very unlikely that it's true, right? But when you've got something like the Riemann hypothesis that has resisted solution for a long time, you start to wonder, well, maybe it is undecidable, although I think it's probably not. The Mosley's theorem was open for a long time, and that was proved in the 1990s. But anyway, so this is kind of the last bit of kind of strange set theoretic culture that I'm going to expose you to is our mathematics. Not only does it have some holes if you're not careful, but it has to have holes. You've got a finite set of axioms, so there will always be something that is undecidable. And if you really need it that bad, if it's really undecidable, you can just throw it into your axioms and prove the theorem. Okay, any questions? Okay, for the rest of the course, the next few weeks, what I'm going to do is I am going to give you all a running start into a couple of the courses that you may have. Almost everybody in here has to take some abstract algebra and either real analysis or advanced calculus. So I'm going to give you kind of a running start at that. Now I've given you the tools in 3190 to kind of, tackle some mathematics. So let's do this from a practical point of view. Hopefully this will give you a leg up. And if I actually finish early, which may not have, then maybe we'll come back to the algebra. I'm going to show you some other kind of cool stuff. Okay, so first thing we're going to look at a little bit of abstract algebra. I'm going to start by looking at something called a group. Before I do that, I'm going to have to introduce something that's sort of fundamental to me. Let S be a non-empty set. A binary operation on S Yes, a function. It's a function from S cross S into S. Okay, this looks like rather abstract, but think of it this way. A binary operation is a function. It's got two inputs. And it gives you an output in S. Right? Sort of binary operation is two inputs from the set and it spits out something. You all, well, let me give you a set. Take the integers. Can somebody give me an example of a familiar binary operation on the integers? A way to take two integers and get another integer. Add. That is one example of a binary operation. Take two integers, the output is just add them up. Right? Can you name another one? Multiplication is another one, right? These are examples of binary operations. Let me give you some more. Addition, multiplication, actually subtraction even, are binary operations. On many things. Natural numbers, the integers, the real numbers, 2x2 matrices, right? Y'all remember from linear algebra, you can multiply two 2x2 matrices and get a 2x2 matrix, right? Notice multiply, add, natural numbers you get, multiply, add, these all give. I did mention subtraction. I didn't write it down there. Subtraction is a binary operation on all these sets except for one of them. Which one is it? Not a binary operation. Which one? The natural number, right? Here's the problem. If you define the binary operation to be input, you just subtract them, you might end up with actually a negative number of 0, right? So, and why didn't I write subtraction up? Multiplication and addition are better behaved than subtraction because when we talk about binary operations, we're not going to just want any function. We're going to want it to have certain properties. Here's another one. Do that. Function composition. That's a way to combine this and you get a new function from R to R. So I'm going to make this definition myself. I've used this terminology, I think, a little bit. I'm gonna make it formal here. I am going to find something that I'm going to call an algebraic structure. Find an algebraic structure. A, B, well, is a non-empty set if or more binary and perhaps some relations. Okay, so let me give you some. I'm gonna call this GL2R, this means general linear group, doesn't matter, that's just school language. What am I considering here? Just 2 by 2 matrices that have the property, by the way, what does that mean? That's exactly, I like that answer. She said it's invertible, right? So the determinant is not 0, so that means it's got an inverse, right? It's got a multiplicative inverse. Can anybody name a binary operation on this one?
Addition.
That's, addition actually doesn't apply here. There's a technical problem with it. Do you know what it is? What's the easiest invertible matrix you can think of?
Yeah, identity.
I agree. What's the second easiest?
2 times the
Right, but I'm gonna do this. These are both invertible. Like, what happens when you add them? It's not invertible. That's the problem. So if you add these things, it might not be a binary relation because when you combine them, they're no longer in the setting. But what can you do to keep that set? You can multiply. But if A, B are invertible, then so is AB. So if I have an invertible matrix and an invertible matrix and multiply together, it's a new invertible matrix, right? Does anybody know how you can prove that the product of 2 invertible matrices? Or what's the kind of a linchpin behind why this is true? Let me ask you this. Let's say the determinant of A is 4, the determinant of B is 12. What's the determinant of AB? It's 48, isn't it, right? Determinant of the product of 2 matrices is the product of the 2 determinants, right? Which means that when you multiply 2 matrices that have a non-zero determinant, it's still got a non-zero determinant. Everybody agree with me? I did say 1 or more on your function. Anybody name a set with a couple of binary functions on it? Anybody think we'll play it a place? a set where you can add and multiply?
But in actuals, there was the, 2x2 matrix not necessarily, but the 2x2 matrix is not necessarily invertible.
Oh, okay. Hey, I see where you're going with that. Oh, okay, so I'll use your example. Let, uh, so what Daniel's saying is, why don't we just throw out this crap without having a non-zero determinant, right? What happens if you take two 2x2 matrices and add them together? What do you get? Another 2x2 matrix. I no longer care about the term. What happens if you multiply them? Still a 2x2 matrix. So absolutely, this works. Notice the addition order doesn't matter, but multiplication sometimes does. Let me give you so this says addition and multiplication. And notice, so this is kind of a blast in the past. How many of you saw this identity in 31? They probably did it from the other side too. It wouldn't matter. This is kind of mixed. Basically, did anybody know what this property is called? It's the distributive property, right? And really what that does is that just the distributive property says we got two binary functions, right? Addition and multiplication. And this is, well, one of the pieces of the distributive property that says they play together well, right? That's essentially it. Let me simplify this. Ordinary integers has two binary operations, right? You can add two integers and it's an integer. You can multiply two integers, it's an integer. And it plays well as well. What did I say about past simulations? Sometimes you get even more structure, we've seen that. C can also be ordered, right? That is to say, so I can add two integers, I can multiply two integers, and actually I can totally order, right? So that's what I mean by sometimes algebraic structures have some other relations on them, in this case, an ordering relation. Okay. With this in hand, I am going to consider a fundamental algebraic structure called definition something. 6.5, I guess. For my definition of group, I am going to define the binary operation by circle, right? That's the way that's my function. As we progress in our knowledge of group, I'm quite a bit lazy. Instead of writing circle, I'll just put two elements next to each other to denote the function. So first thing, I demand that this is a non-empty set, G, equipped with a binary function circle, which is our map from G cross Q and G. So this is just a way to combine two things. satisfying, I'm gonna call this first one 0, and then I'll tell you what I'm going to do first. G1 circle G2 is in G for all G1, G2, G1. I don't want just any binary part. I don't want just any binary function or any way to combine two elements of G. I needed to have a little pizzazz. I needed to have something that works well. First thing I'm going to demand anybody know what this property is called? Try to do some memory association. This is called the associative. Two, I want, there exists an element E in G. It is a very special element because E composed with any element of G is G for all G and G. So I've got what we call an identity element. That is an element that leaves everything alone. And finally, for all G and G, there exists H and G such that G combined with H in either direction is the identity. And sometimes we call H the inverse of G. So this is what it means to be a group. It is a set where you've got some method of combining two, that's the binary relation or binary function thing. You've got some way to combine two things such that you always end up back in the set, right? That was the problem here. For this example, addition was not a binary function because when you add these two, you get the zero matrix, which takes you out of the set. Right? So there's a way to combine two things so you stay in the set, and it behaves under some nice rules. Number one, it's got to be associative, right? I mean, it is just the Wild West. That's not true. There's a special element called the identity, such that when you combine any element of the group of the identity, you get the same thing back. And given any element, there is a way to take it back to the identity, right? You can combine G and H in either order, you get back to the identity. This is the existence of the inverse, right? So, my first statement, given the preamble here, the reason I wrote that as statement 0 is it's redundant, right? I just put it there for emphasis. Why did I really not need to write 0 there? This statement right here. Because this is a binary function in the first place. So if this is a binary function, this is always in G, right? So this statement is redundant. I just put it there. Okay. Let's look at this first example here. Let's think about this. We've already seen that adding two things up here is not a binary function, but what if we multiply it? Okay, so ask yourself this, let's go through the list. When I multiply two by two matrices that have a non-zero determinant, what do I get? Do I get a donkey? No, I get another two by two matrix, and what can you say about its determinant? It's not zero because it determines the two elements of the product relation. Okay, check. Is matrix multiplication associative? It is associative. What is it not? Yeah, commutative. AB and BA might be different things. They could be different things, right? But notice in my list there, I didn't ever demand that order couldn't matter, right? It certainly is. You probably learned, you might not have had this proved for you, but probably you did learn that in fact, this is true for any matrices. It doesn't have to have non-zero determinant. Right? If you have A, B, and C all make n by n matrices, then you always get. So we got this one there. For this particular example, what is the two by two matrix that you can combine with any other matrix? And here by combine, I mean multiply. And it leaves it alone.
Right, and you it's 1, 0, 0.
Good. And it doesn't matter which side, does it? The identity on either side multiplies just like it says over here. How about the inverse? Wait. A, C, D. Anybody remember what this is? I always have to think about this thing.
D over A minus BC.
What's it?
Was it first D over A minus BC?
Yeah, it's something. I swap these out, it's A. It's minus or something. I may be writing this down wrong, but I'll fix it if I do. Let's do AD, minus BC. Yes. AD minus BC, that's right. So the determinants which we want. So it's going to be AD minus C. That's going to be 1. That's going to be 0. That's going to be 0. I can call. That's what the inverse is. How many of you have seen this probably? Notice when you multiply A times this, you get the identity from either side. So this set is a group under multiplication. And the order does matter because if you invert the order of the matrices, then you could potentially change things. How about two by two matrices under addition? Well, what happens here? This is A plus B. If I add two by two matrices, do I get two by two matrix? No problem. So this is, by the way, sometimes this is called closure. Combining two elements of the set, you can element set. Addition of matrices is associative. What's the identity matrix here? What's the matrix that you can add to any other matrix and leave alone?
Zero matrix.
There you go. Under addition, that's the identity. When I add the identity matrix, any matrix, it leaves it alone. Right? And if I have then A inverse, if you will, is actually what can you add this to this matrix? It gives you the zero matrix. That is correct. It's the minus. So 2x2 matrices form a group under addition. 2x2 matrices that have a non-zero determinant form a group under multiplication. Let's look at some other examples. Of course, you all kind of led me down the path, started with more sophisticated. Here's an example here. Here's an example of a group. The integers under addition. What happens when you add an integer to itself? You get it, or add two integers, I should say. You get another integer, right? Addition of integers is associative. Addition of integers has identity 0. And the integer n, its inverse is negative n. It's additive inverse. These are all groups. What about the integers under multiplication?
You don't always have multiplication.
Yeah, you're ahead of me there. That's right. If you multiply two integers, do you get an integer? Sure, no problem there. Is multiplication of integers associative? No problem there either. It's even got an identity. What's the identity for multiplication of integers? 1. If I agree with that? Here's the real problem. Under multiplication, which integers actually have inverses that are still integers? There's one. Under multiplication. One has an inverse. The other answer is still negative. Right. Only two integers have inverses, multiple inverses. They're actually still integers. Right? This is problematic. 2, 3, 4. None of these have inverses that are integers. Well, maybe I can fix that. What about is this a group? If I multiply two rationals, it's rational. All right. Multiplication of rationals is associative. The identity is 1. What's the inverse of the rational number A over B? B over A. So this is a group, right?
What about 0?
But what about 0? Stupid 0. That's the only one that messes it up, right? Every other rational number, no problem. How can we fix this? I love this cheat. The non-zero rational numbers under multiplication is grouped. Right? Let me ask you all a question here. Anybody give an example? Every one of the examples I've given, every one of them. All groups. Can anybody give me an example of a finite group? Okay, I'm waiting for the smart aleck answer. There's a smart aleck answer to this. What's that? I'm sorry, what? Oh, I think I know what you're saying. Let me give something less abstract than you did. How about the set zero under addition, right? I mean, how silly is that, right? 0 + 0 is still 0. So I feel like a total tool talking about the properties here. Certainly 0 is the identity and it's also its additive inverse, right? How about 1 under multiplication? How about ± 1 under multiplication? How about when you said I, you meant the identity, am I correct?
I was thinking that the complex number.
I can make that work. How about the set of 4 things under multiplication? I should fix 7 things. When I multiply any pair of these, it's still in the set. Check it, it's not too bad. Notice, multiplication is associated because these are complex numbers and complex numbers have associated multiplication. 1 is the identity, and I'll show you who everybody's inverse is. 1 is its own inverse, so is -1, and these two are inverses of each other. All right, so there's a group of 4 things now. Okay, can anybody give me an example of a group with n things in it? For any n?
Zero and there's up to -1.
Oh, that's a great idea. And what's my rule for adding them?
That's back.
Let's start with the clock, shall we? I'm gonna do a special case of what it says. Let me tell you. This is called Z mod 12. Hopefully you'll see the pattern. I'm gonna take these symbols and I'm gonna add them, what I'm gonna call this addition mod 12. What's the rule here? Take these two and add them up. Add A and B just like ordinary integers, and then take its reduction mod 12. What do I mean by that? I mean, add them up just like ordinary integers. If you don't exceed 12. Right, because 3 bar plus 4 bar, 7 bar, 7 bar is still in that set, right? But if I run into trouble, what is this? 17 bar. How do I interpret that? That's not the setting. What should it be?
5.
10, 11, 12, 13, 14, 15, 16, 17. So that's the way it works. Now, can anybody tell me how I could have done that quicker than counting like an idiot over and over again? What's a shortcut way to figure out what 17 is, mod 12? Subtract 12. More generally, if I give you a worst part, so what if I did this? If But something like this, so this is 15, 26, 29. and this is 14. How could I do this quickly and it not count over? Subtracting 12 won't cut it, because 30 is still not in the set. Correct. Divide this by 12 and figure out what the remainder is, right? It'll be 36, so this should be 6 bar. So you divide by, in this case, my mod is 12, take the remainder, and that's what's left over. This is actually a group, right? Because when I combine any two elements, I get something either in the set or that's looped out, and it still determines something in the set, right? Let's see. Is it associative? Yes, it is, and it's associative for the same reason that adding integers is associative. You might try to prove that. It's a little tedious, but it's not terrible. What is the identity element? What is the element that you can add to anything and it leaves it alone? How about the 0 bar? What about inverses? What's the inverse of A bar?
12 minus A.
That'll work. 12 minus A, negative A bar. Negative A bar is probably not in the set, but we've discussed how you can get it back. I'll show you what the inverses are. This is its own inverse. 1 and 11, 2 and 10, 3 and 9, 4 and 8, 5 and 7, and 6 is also its own inverse. That's kind of weird, right? 6 plus 6 is 0. Any questions? Do y'all see how to generalize this? If this is a group. And I like to think of this first one as a clock, and this is a more general clock, because what happens if it's 10 p.m. at night? What time is it 3 hours later? It's not 13 o'clock, it's 1 o'clock. Right? You loop around. Okay, any questions? Example here. Okay. Yes. Okay. But I'm gonna do this special name for now. I'll just call this G. We'll say this is my name. So that's yes.
Is that for mod like N? Does that work? Like, could it also just be the naturals? No, they'll always be like that.
Well, it loops around. See, these all occupy both positive and negative, right? So for example, right here, 1 bar is the same thing as 13 bars, the same thing as 25 bar, it's the same thing as negative 11 bar, negative 23 bar, and so forth. So you're subsuming a lot of stuff here. Suppose you have the set of bijections from F to F, right? What if you combine them by composing, all right? If you have a bijection from S to S and another bijection from S to SG, isn't the composition also a bijection? Okay, so it's closed. Is function composition associative? Yes, we actually proved that in this class. There's the identity function from S to S, that's the identity. And what's true about a bijective function? If you have a bijection from S to F, if F is a bijection from S to S, isn't its inverse also a bijection? This actually forms it. And in fact, if you think about this guy here, if you start with this, what is a bijection? Well, if I do any scramble that I want to a Rubik's Cube, what have I done? It is a bijection of the pieces to the pieces. All the corner places went to a new corner, side places may have gone to the sides, the center stayed the same, whatever. This forms a group. Now, the combinations on the Rubik's Cube, the scrambles on the Rubik's Cube form a group under function composition. We'll talk more about that next. Any questions? All right. Well, again, I encourage you all to be at the math club this Friday. It's basically the talk is going to be how to use ODEs to not kill your goldfish. It should be an interesting